Hey everyone, and welcome back for another deep dive. Today, we're going to be looking at DC motors.
Ooh, fun.
Yeah, these are everywhere, right? You see them in fans and toys and cars and all sorts of things.
Absolutely. And they all work because of these amazing principles of electromagnetism.
So maybe you've wondered what exactly is going on inside a DC motor.
Well, we're going to break it all down for you.
That's right, we're going right to the source. There's this great open educational resource from Singapore called Direct Current Motor, or DC Motor, in 3D WebGL JavaScript HTML5 applet simulation model with Boonsheen.
That's a mouthful.
Yeah, well, it's got a really cool interactive simulation that lets you actually visualize how these things work.
Yeah, it's really helpful for understanding the concepts.
So let's get started.
All right. So to understand DC motors, we first got to talk about the basic components.
Okay.
So first you have the stator.
The what?
The stator is basically a stationary magnet. It just sits there. And it creates this magnetic field, with those invisible lines of force running between its north and south poles.
Right, right.
Okay, now we've got the armature, which is also called the rotor.
Mm-hmm.
And this is the part that actually spins.
Ooh.
And basically, it's a coil of wire, but when an electrical current runs through it, it becomes an electromagnet.
Okay.
So now we've got two magnets, right? We got the permanent magnet, the stator, and then we got this temporary magnet, the armature, which is only magnetic when the current's flowing.
Right. So these two magnetic fields are interacting with each other.
Exactly. And that interaction, whether it's attraction or repulsion, creates a force on the armature. Now think about when you're trying to turn a wrench or something. That turning force you apply is called torque.
Okay.
Well, in a motor, the magnetic forces create torque on the armature, making it spin.
So it's constantly being pushed and pulled by these magnetic forces. But how does it spin continuously? Why doesn't it just swing back and forth?
Well, that's where the commutator comes in.
Commutator.
Yeah, it's this clever little device that connects the armature to the power source, like a battery. And the key thing is it reverses the direction of the current flowing through the armature every half cycle.
So, hold on. Why is reversing the current so important?
Okay, picture this. The north pole of the armature is attracted to the south pole of the stator, right? That gets it turning.
Right.
But if the current keeps flowing the same way, the armature would eventually stop once those poles line up.
Oh, see.
So what the commutator does is it flips the current, which in turn flips the magnetic poles of the armature. So now instead of stopping, the armature keeps being repelled and attracted and keeps on spinning.
Oh, that's really cool. It's like a little dance they're doing.
Exactly. And speaking of directions, there's this thing called the left-hand rule that's really helpful for figuring out which way the force is going to act on the armature.
Okay, tell me more about this left-hand rule.
Well, imagine holding up your left hand with your thumb, forefinger, and middle finger all sticking out. Your forefinger represents the direction of the magnetic field. Your middle finger points in the direction of the current in the wire, and then your thumb shows the direction of the force.
Oh, wow. So if you know two of those things, you can use your left hand to figure out the third?
That's exactly right. It's a handy way to visualize what's happening.
I bet our listeners are all holding up their left hands right now trying to figure this out.
I hope so. It's a great way to make it more tangible. And, engineers actually use this rule all the time to design motors.
Oh, wow. So it's not just some theoretical thing.
Absolutely not. And that's one of the things that makes this simulation from Singapore so cool. You can actually see the magnetic fields and how they interact and how that left-hand rule plays out.
Yeah, that sounds really cool.
Yeah, it really helps you visualize it.
But before we get too deep into the weeds here,
Okay.
we've been talking about using electricity to create motion, but what about the opposite? What about using motion to create electricity?
Oh, you're talking about generators.
Yeah, exactly.
Well, that's a whole other fascinating topic, and it's actually closely related to what we've been discussing.
Wow, this is getting good.
It really is. We're going to flip the script and see how these same concepts can be used to power our world.
Yeah.
So stay tuned.
This is exciting stuff. Don't go anywhere. We'll be right back after a short break.
So we've been talking about how DC motors use electricity to create motion.
Right.
But now let's look at generators, which do the opposite. They use motion to create electricity.
So we're reversing the whole process.
Pretty much. And it's actually a really simple idea at its core.
Okay, I'm listening.
You just take a coil of wire and spin it inside a magnetic field.
Okay.
And that creates an electrical current in the wire.
Wait, so just by moving a wire in magnetic field, you can generate electricity?
Yeah. Well, it's not quite that simple, obviously.
Right.
There's a lot that goes into making a really efficient generator, But the basic idea is that simple.
This makes me think of like those hydroelectric dams where the water spins those big turbines.
Exactly. That's a great example.
So the falling water spins the turbines, which then spin a coil of wire inside a magnet, and that generates electricity.
Yep, that's how it works.
But I thought those big power plants generated AC power, the kind that comes out of our wall outlets.
That's true. A simple generator like we've been talking about does produce AC.
So how do you get DC power then?
Well, you can use a commutator just like in a DC motor.
Oh, right. So it can convert AC to DC.
Exactly. It all comes back to those same principles of electromagnetism.
So to recap, we've got DC motors that use electricity to make things spin, and then generators that use spinning to make electricity.
That's a great summary.
And they're both based on these same principles.
That's right. And they're used in so many different applications. It's really amazing.
It is. I never really thought about it before, but now I'm seeing DC motors everywhere.
It's like you've unlocked a secret code.
Yeah. It's like seeing the world in a whole new way.
I know what you mean. It's really cool.
Okay, so we've talked about the basics of DC motors and generators, but are there different kinds of DC generators?
Oh, yeah, definitely. There are a lot of different designs out there, all using different ways to spin that coil of wire.
Oh, like what?
Well, there are wind turbines that use the wind to spin the coil, and even those hand crank generators you can use in an emergency.
Oh, yeah, I've seen those.
It's all about finding different ways to harness energy and turn it into electricity.
That's pretty awesome. It seems like there are endless possibilities.
There really are. It's a really exciting field to be in right now with all the new technologies being developed.
Yeah, and it's all based on these same basic principles that we've been talking about.
It's amazing how much you can do with just a few simple ideas.
It really is. Learning about how things work really makes you appreciate the world around us even more.
Absolutely. It's like you're peeling back the layers and seeing how everything fits together.
So we've covered a lot of ground today. We've talked about how DC motors work. We've explored the world of generators, and we've even talked about some real-world applications.
It's been a great discussion.
But before we wrap up this deep dive, I have one more question for you. Remember earlier when we were talking about that left-hand rule
Yeah?
and how engineers use it when they're designing motors?
Right.
Do you think someone could use that rule to, actually build a simple DC motor?
You mean like from scratch?
Yeah. Like if you had a battery and some wire and a magnet, could you put it all together and make it spin?
I think it would be a pretty fun challenge.
Yeah. It'd be really cool to see if you could actually get something to spin using just household materials.
I think it's definitely possible. All those little science fair projects,
Yeah.
a lot of those are based on these same principles.
It would be amazing to build your own motor and see it actually work.
It would really give you an appreciation for how these things work.
Yeah, for sure.
Yeah.
So what do you think? Could someone build a simple DC motor using just stuff they have around the house?
I think so, yeah. It would take some ingenuity and some trial and error,
Right.
but I think it's definitely doable.
That's so cool. I'm almost tempted to try it myself.
You should. Maybe we'll inspire some of our listeners to give it a shot.
Yeah. If anyone out there builds their own DC motor, we want to hear about it.
Definitely. Send us pictures and videos.
We'll post them on our website.
And speaking of our website, we've got a bunch of resources there for anyone who wants to learn more about DC motors and generators.
Oh, right. We'll put a link to that Singapore simulation we talked about.
Yeah, and we'll also include links to some other great articles and videos.
So if you're interested in digging deeper, you know where to go.
And who knows? Maybe this deep dive will spark a lifelong fascination with electromagnetism.
I hope so. It's such a fascinating topic.
It really is. There's always more to learn.
Well, that about wraps up this deep dive into the world of DC motors and generators.
It's been a fun journey.
We've learned how these incredible devices work.
And we've seen how they're used in so many different applications.
They really are essential to our modern world.
Absolutely.
Yeah.
And who knows what the future holds?
Yeah, maybe one of our listeners will be the one to invent the next big thing in DC motor technology.
That would be amazing.
All right, everyone, thanks for joining us on this deep dive.
See you next time.
And until then, keep those minds curious and keep exploring.